So today I'm going to talk about this ZK Snark message board. Basically, this is a project that me and Nick Elvin did over January. And in kind of ePrinter, we discussed a lot of like how we did the solidity and how we actually set up the contracts. But I thought it would be kind of more interesting to discuss how we did the actual zero knowledge construction, which I think is particularly interesting and pretty. So yes, I can send it to you. So you can imagine the setup of the problem is you have a bunch of users and you have some group creator. They create some group on chain, and then off chain there's some group you want to represent that all share a password. Maybe it's MIT students posting on MIT confessions. Maybe it's Twitter blue checks that all kind of share a password and want to post on behalf of all Twitter blue checks. And the idea is then you share this password amongst that group, and they anonymously join the group on-chain and post anonymously on-chain as well. And because they're kind of on-chain guarantees, they can prove that all the stuff is anonymous. And so you can imagine that this kind of results in all of the properties you want to have. Your contract has create, join, and post, and you verify all the anonymity and that everything is real and as you expect. Great. So let's try to think about how different ways that we construct this scheme might work or not work and work towards our final ZK model. Okay, so let's start with the first initial, most basic version of this idea. We don't want to reveal the original password, so imagine the smart contract stores the hash of the group password, and we send it the hash of the password along with our public key. So then you can imagine the smart contract adds our public key to a list of allow listed public keys. And in the future, if I ever sign a message with my public key, the contract can verify that, yes, I'm in this allow list. I must have sent the hash of the password before. I must know the password. And so they can decrypt my message and say, or they can verify the message and say, yes, this was sent from someone from the group. Okay, so this is a very flawed idea for the construction we want to make. So does anyone have any reasons for why this might be flawed? Feel free to yeah,
I guess anyone knows what the hash of the password is.
Yes, okay, so the first issue is the hash of the password is public, so in the future, anyone can just use the same hash of the password. Okay, there's some more issues with this. Anyone?
It has the public key in it?
Yes, it has the public key in it. And actually, it's not just that we sent the public key, it's also saved on chain in this contract. It's also sent from my public key, so the user who's joining kind of reveals it in the transaction. And then finally, we sign the message with the public key. So you can imagine that in order to verify the message is actually signed correctly, you need to know the public key. So the public key is kind of revealed in 3 places, which is really annoying. So first, we're going to resolve this password issue, and then we'll deal with all the public key stuff. And hopefully the password issue will illuminate some insights on also how the public key stuff might work. Okay, so these are kind of the issues we talked about. Great. So, okay, so now to resolve the password issue, this is kind of pretty standard. We add a nonce to the password. And so, as before, any user can send the hash of a specific password, and the chain verifies that that password will not get used again. And so only the first person who ever used the password can get into the contract and add their public key. Okay, so now on the password side, does anyone see any issues with this?
How does the server verify or the contract verify the password?
Yeah, so you can imagine the contract just hashes the hash of the password and verifies the same as the string that it stores. Yep. Cool. So this is basically completely secure, except for one small thing I'll talk about later. But we can imagine this is a fertile ground to demonstrate how a ZK proof might work. To additionally show that, for instance, we know the original password. So imagine this construction, where we do this similar thing, but in addition, we send a ZK proof showing that we know the pre-image of the hash password. That is, we know the original password. And you can imagine the structure of a ZK proof, if you're not familiar, is you have some public and private inputs and a public output that is a hash of the password, and you can prove that you did the computation. So basically, you can prove that this password resulted in that hash password without revealing the original password. And so this doesn't actually add any security or anything to the existing password protocol, but it's a good proof of concept for how a ZK proof might work here to additionally show that we know the original password. Great, so you can imagine that the contract now when it's created needs to have a bunch of hash passwords in it. For instance, if you have 16 hash passwords, that means 16 people can now join this smart contract group. And I don't actually know how DF invite key system works, but I imagine it's some similar smart contract thing. So there is kind of one small thing here where if you send these transactions, you can actually front run them because someone can just be like, oh, I see this hash of the password and the ZK proof. I'm just going to copy it to a different transaction, substitute my public key in, and front run it. And so there are a couple ways to resolve this. You can like publish a commitment in a previous block. And so the contract can verify that, oh, I will only accept people who published, say, the hash of this whole transaction in a previous block, meaning that in that block, you can't be front run because someone else would have to have published the same hash beforehand. But we don't actually need this, and the front running issue is kind of resolved in case you were thinking about that. Okay, so hopefully that made sense. Did anyone have any questions on kind of the password section, how we did any of that? Okay, cool. So now on to how we resolve the public key issues and keep that all anonymous. Okay, so recall our original idea where we use the password scheme to verify who we are, and we add ourselves to a list of public keys, we sign a message, and we send the transaction from the same valid public key. So let's kind of focus on one at a time. Let's first resolve the fact that all of the public keys are public in the contract. Okay, so kind of similar to the way we like obfuscated the password by hashing it, let's try that with a public key. So we're gonna have the smart contract have a bunch of hashes of all the allowed public keys, and to the contract, we send a ZK proof that we know the pre-image of one of these hashes. So you can imagine the way this proof works is you have something like, you want to verify some equation that looks like this, where like A, B, C, D, all the way to Z are, say, all the numbers in the smart contract, and X is the hash public key. That's one of the private inputs. And so you can imagine that the kind of main thing your ZK proof is verifying is that this multiplication equals 0, right? Because at some point, you have like X minus X, and this is going to be 0, meaning that you are a member of the original list of the hash of all the public keys. Right, so hopefully this makes sense that you can prove that you are a member of a list. And at the same time, because this is all in a ZK proof, you can show that your public key is like a private input as well as the hash of the public key. So no one can kind of identify who you are. Okay, so there is an issue, kind of an issue with this where someone can de-anonymize you. Does anyone know how that still might be possible just through the contract? Any ideas? Just knowing the hash of public keys, how might someone de-anonymize someone? Okay, so this is a little bit tricky. This also took us a while to get. But basically, it's actually possible to figure out the pre-images of these just knowing the hashes because the anonymity set is quite small. Like there are only 245 million Ethereum public keys at all. And so one could just hash all of them and check, okay, these are the ones in the smart contract. And so it's not actually as anonymous as you might think. Okay, so we need something slightly better. So let's try instead, we hash the public keys and some random salt string. And now, in order to, when I send a message to this contract, I prove that I know the pre-image of both the public key and the salt. Okay, so now someone can't do that anonymity attack because they would have to know like this random salt string as well, which could be anything. And if it's long enough, it basically makes the contract side secure. So we still have the two issues of sending as the public key and signing the message. Okay, so first let's attack the sending as the public key. Okay, so you'll recall yesterday, if you guys were here, there was a talk on the gas station network and how it basically uses relayers. And if you paid attention, there was a point where Justin mentioned that the relayer actually signs the message for you and then sends it. So it turns out that if we send the message through a relayer, then this relayer will sign the message, and so we won't actually reveal our public key. And we can kind of, the usual relayer protocol includes the public key in like the message of the transaction, but we can use relayers, for instance, that don't do that. And this way we can basically stay anonymous and send it to the contract without revealing who we are. There is one small unintended consequence of this that is not completely obvious, but it's that basically if we only verified public keys, then you could just choose anyone's public key and do all this calculation because you don't actually need the private key here. Right? You're only adding a public key to some allow list. So the kind of usual way that like Ethereum solves this is you prove you have the private key. Right? But the issue is we can't prove we have the private key here because we don't want to reveal our public key or private key or any of that stuff, because then they know who we are. So now we have this additional kind of issue that that we don't really know how we're going to sign, and we need to prove that we have this public key. Okay, so this is where the ZK proof gets kind of crazy. So previously, our ZK proof just showed we had the pre-image of this public key, this hash of the public key in the salt. So then we had the public key in the salt. So this kind of this original ZK proof verified that we knew this public key and this is the correct public key. However, in order to prove that we have the public key, we also need to prove that we know some private key that becomes this public key. So you can imagine if we, like, for instance, verify we sign some random string and we prove that the signature, we sign it with our private key and we prove the signature checks out with this same public key in the same proof, then we have the private key. Additionally, you could also just, like, for instance, generate the public key from the private key in the proof. But basically just some scheme in the proof that also proves you know the private key. Okay, so now we've kind of solved the anonymity of the sender. But there is kind of one last thing that we need to also do with the message, where the message needs to be signed. And you can imagine that if we have this private and public key already in the ZK proof, you can kind of imagine how this last slide is going to go, where we keep expanding this ZK proof. Okay, so final construction is here. The contract has a hash of the public keys in the salt, and we add an additional thing to the ZK proof. So here we could, for instance, in the ZK proof also attach the signed message. But because here we've proven that we have the private key and the public key, and these are allow listed because we know the password, we can just attach the message directly. We don't even need to sign it at all because we've already proved that we have the public key and the authorization to send from it by proving that we know the private key. Cool. So you can imagine now when the group when the group creator is creating it, they kind of have two options. They can distribute all these passwords, or just directly add the hash of all the public key. We can do it like this can just be any random salt and that to be the password to the contract. Cool. Are there any questions so far before I wrap up? Yes.
Does the salt change every time you want to post a message, or do you keep the same salt?
Well, you'd imagine that if the passwords are one time, you can keep the same salt. There's actually no disadvantage to using the same salt again.
Cool. Why is this not vulnerable to replay?
Well, if they replay this transaction, they're only going to be able to prove that your private key and your public key are allowed by this password. Because in order to, for someone else to replay the transaction with kind of their password or their private key, they would have to publish like their own ZK proof. And basically, the solution to that is if we include the password in the ZK proof. So for instance, like if the salt is the password, like here, then you can show that's also part of the ZK proof.
And the message is signed with, I guess, like, okay, my model of this right now is that you're going to send like the hash and the ZK key, and then the message is just going to be there in plain text. I feel like I still don't understand why you couldn't just like send someone else's hash and their ZKP and your own message.
How is the stuff you send intertwined with the message?
Right. Okay, that is true. Why can't someone just replay the whole thing and just attach a random message? Okay,
Or even if they are intertwined, they could, in theory, send the same message again and make it seem like you sent the same message.
Yeah, exactly. So, right. So basically, the way you resolve this is within the ZK proof, you also attach an additional step where you sign the message and also decrypt the signature, prove that that was the message you signed. And so, kind of the message we were talking, the random string that kind of we're signing here to verify the signature, like this would kind of be the message in order to also verify that this construction works. Does that make sense? That if we kind of like are verifying, like we're signing the message within the ZK proof and then proving that our public key and private key signed it, and we have like some timestamp on it, for instance, to avoid
like a nonce or something.
Yeah, or like a nonce or
Basically, you
something.
can always stuff each additional piece of identifying information and then
Inside
also,
the ZKP. Exactly.
It's
Yeah.
like literally a pattern the entire time, right? It just keeps
Yep.
expanding until
Yeah,
all included.
exactly.
But technically, from what's there, I think what Robert was saying
Yes.
was like, yeah, you also just need to include those other
Yeah,
things.
exactly. You also need to include, so kind of like, I was kind of using the word random string before, but basically like the final proof instead of the random string would have like the message and something like nonce.
Yeah.
And this would basically allow you to prove that the message is unique. Cool, yes.
So is it fair to say that so the nonce for a given password is constant in the contract? So you could tell that the same person is posting a message with this system.
Yes, that is true. That if well, okay, so the issue is that also like this. Yes, that is true. Each password will only work for one message.
Alternatively, you could also like make it so it's just like a commitment to all hashes that are on chain, like a root or something like that. And then you could,
Right, exactly. And you could just do that. Yeah, that would also work. Yes.
Can you remind me what the relay is for?
Right, so the relayer is because when we send the message and we're signing it with our public and private key, like the original idea is that you're kind of using your public and private key. And so if you want to like send without creating some new ETH address, something the easiest way to do this is send it to the relayer and have the relayer sign it anonymously, or else it'll be associated with like some ETH address. Right? Because if you're using your own ETH address, then you have to add gas to that ETH address, and that gas has to come from somewhere, and so you can kind of be traced.
And what are your assumptions about the relayer? I mean, you have to make some, right? Like, basically,
Yeah.
they're not logging everything. And then
Yeah. So the relayer is
it's like
kind
a
of
VPN.
the relayer is kind of this like trusted third party. You can use something like Zcash or Chaindocash Cache in the middle as well, so like anonymize, and that would also like kind of remove all the trust that you're even putting in the relayer. So that's kind of like an additional obfuscation step. Cool. So it seemed hopefully people kind of understood the kind of full construction. Went over it mostly in the last slide. Cool. We actually had a demo where we implemented this whole thing as well. It's kind of bare bones, just like the front end. We just like create, it's like exactly what you'd expect like a UI for this to look like. It's just, the demo doesn't really have like any of the, doesn't actually prove that we did any of this with ZK. It just shows like what the front end interface would look like. But like, if you look on our GitHub repo, everything is happening in the background using $0 proofs. So yeah, there's not really a way to show that.
How big is the like proving key and stuff?
I don't exactly remember. I can check the GitHub right
Is
now.
it as big as like ZK Dungeon? Like,
No, it's nowhere near as big. Yeah, it's like much smaller because there's only like a couple of things that are doing here. This thing spins for another. Okay, there we go. Great. Any more questions, feel free to ask.
Anything online?
Yeah, so specifically like, yeah, so if you want to check out our code, verify this stuff actually happens in the background, you can go to our GitHub repo. It was initially called ZK polling because we built this off of like kind of a simple polling app where you just post, where you're kind of like voting for a candidate and you do ZK to you have all of the guarantees that you want. And we kind of adapted that repository to do this group posting instead. We didn't change the name, I guess.
I have a different style of question, but
Yes.
like, I wonder, this feels like kind of new primitive, right? Like a
Mhm.
permissioned, anonymous group.
Yeah.
I wonder where they'd be useful.
Yeah, so we did come up with the kind of two, like the MIT confession, the Twitter thing. We weren't super sure where exactly it could be useful. They're kind of like you can imagine maybe like if you have like journalists or something reporting from some like state that monitors all the communication, you want to prove that you're like from the journal organization and you're posting to like from the New York Times or whatever. You could also use this to anonymously post and make sure that then they wouldn't know that you're in the state.
Or like a whistleblower or something.
Exactly, any whistleblower, any group like that. But yeah, I am. If you have any ideas for where this might be used, I'm open to hearing it.
Yeah, whistleblowers.
Yes, I think so. someone else had a question somewhere.
Who runs the, like, who decides what gets into the contract whitelist?
So there are two ways you could do it. One is you could send each user that gets the password could send their hash of public key and salt to the group owner who adds it to the initial contract. You could also just use the password, and when you verify with a hash password, you additionally send your that string that gets added to the contract list. Yeah, and kind of as Lachlan mentioned, if you add it to the contract list, you can still you'll know that every message is from the same address, although you won't know who owns that address. You will need a new password for every unique message.
So you kind of skimmed over the front running problem. I mean, if you're generating all the keys yourself, then you're sending them to friends or whatever, you're not going to get front run. But if people are joining yours, the second way you were just explaining, is it just a risk of being front run, or did you actually solve it? You kind of just skimmed over that.
Yeah, so this is a good question. So here, when we attach this, so the password step can still technically be front run.
Yeah.
But if you do the password step at the same time you do all of this, so namely you post one message at a time with a unique password, and this all gets concatenated into one thing, then in that transaction that can't be front run because the person can just the person would then just be showing that your message comes from your friend.
Right. Well, I was thinking about that first password step because I mean that's one of the reasons that Forest has a server, right? So that the whitelist can't be front run.
Yeah, exactly. So if you decouple them, then you have to do the block stack technique to avoid the front run. Yeah. But we didn't actually implement the block stack technique. We just did it instead. I actually don't know if it's a block stack technique. I just read it in a block stack paper. In the block stack paper, this is how they kind of avoided front running. But I'm sure someone came up with it before them. Basically just a commit real.
So what's interesting about this, I'm actually not sure if this is going to be right, but if it's wrong, it might be even more interesting. But so normally, let's say you had a group of journalists or other stuff, and you send each of the people in that group an invite key. In a traditional system, I would be concerned that this site tracks which invite key I use to register for it. A naive flow would be, here's I'll give each of you your own invite key, and here's my new site, and as long as and anybody with a valid invite key can sign up for the site, but maybe the site is actually secretly keeping track of which invite key signed up for each new account, right? That would be your default assumption. But with this, that is not the issue, right? And that I think is a very meaningful distinction in terms of the potential use case. It removes the remaining man in the middle, not man in the middle, but the remaining logging risk. There's some relayer assumption, but like you said, you can also get around that. So you can really be sure that nobody knows and has tracked who you actually are. I think that is actually a pretty interesting use case. The journalist one is obvious, and then there's other cases where it might be the difference between someone wanting to use something and not. Maybe you would just send an invite key to everybody with more than 10 million Twitter followers or something like that. But this construction lets you send invite keys to people, and as long as they believe that this stuff works, which might be the real bottleneck, they can be sure that there actually is no party that can track it. And I think that once people grok that pattern, there will be a lot of cases where it turns out to be the difference between somebody using it or not. Because it is already, I think, a big leap to be yeah, but the point of registration didn't actually track which invite key and then who sent it. So I think that is that alone is a pretty powerful concept. And that is that correct?
Yeah, that's correct. Because this is all
that's what makes this, I think, really special.
Exactly. Yeah, and if some front end does track it, you can just switch to another front end that doesn't.
Because the naive implementation of sending invite keys, that's specifically what that is not able to achieve without this construction.
Yeah, exactly.
There's an interesting use case too for anonymous feedback. There's a lot of times a company or an HR team or whatever will say we want your feedback on this contentious issue, and it will be anonymized. But what they mean by that is you're going to send HR a Google Doc or an email or a Slack, and then they're going to anonymize it before it gets shared with the team. But they still know who you are, and everybody makes mistakes and slips up and has drinks and says who said what or whatever, right? So this is an actual way. Everybody in the company gets the key, and then whether it's a message board or just a singular one-to-one, you you know that it's anonymous, like actually anonymous. But also there's like situations in like private boards and boards of directors and stuff like that where there's like the same problem, like people want to have conversation, but they don't feel like they can share like with the team. They just feel influenced or intimidated, right?
I see.
But this way, it's like for certain topics, if they're highly contentious, your board could have an anonymous debate, an actual anonymous debate, and then and an anonymous vote, a truly anonymous vote after that debate, and then move forward. They kind of like pull out of anonymous land and then move forward with the decision.
Yeah, that's true.
Right, ZKHR win.
Yeah.
All right, I think we should probably close here.